We're going to continue now with our lecture in probability and probability distributions. We're going to enter now the formal definition, or we're going to read the formal definition of a probability. So a probability, formally, if you want to really be, when you want to be a technical, that subject is called probability theory. Okay. So just like, in other subjects in mathematics, another branch of mathematics, number theory, graph theory, set theory. So this is probability theory. So probability itself measures the likelihood of an event, the likelihood that an event will occur. So what are the chances that this event will occur? So probability, you may wonder why there will always be probability with the subject statistics, and when with the subject probability there will always be statistics, because probability and statistics are like husband and wife. Okay, technically, um, probability is the basis for inferential stat. The inferential statistics makes use of the language of probability, okay, in making decisions, okay, because in inferential stat we are making decisions under conditions of uncertainty. Okay, so actually it's the one that bridges differential statistics to inferential statistics. Okay, it's like a bridge between the two branches of stat. So it's really a must that we must go through probability before we can even reach inferential statistics. So it provides a means for measuring uncertainty of decisions and inferences based on data that we have from the samples and experiments that we can do. So let's have some definitions. The probability of an event A, let's call an event A to be any event, denoted by your P of A. P stands for probability. A is the any event that we're talking about. We can call this P of A, or probability of A, is the sum of the weights of all sample points. Sample points are like synonymous to outcomes, all outcomes in the said event. Again, the probability of event A, let A be an event denoted by P of A, is the sum of the weights of all outcomes in this certain event A. Also, we say that, let me erase that, we say that the probability of A can only be between 0 and 1 inclusively, including 0 and 1. So if we can have a 0, we call that an impossible event, because, if you convert this in percentage, this is 0%, right? So if you have an impossible event, it says that it's impossible to happen because it's 0% to happen. If you have a sure event, you can see that it's 1, or if you convert this in percentage, this is 100%. A sure event is the maximum. Okay, it is really certain. You're really sure that it will happen. Our impossible event is our minimum. That's really sure that it will not happen. So the world of probability only lies between these two numbers. When you say 0, it's impossible. When you say 1, it's sure, or it's certain that it will really happen. If you have something in between, let's say this is exactly in between, this is 0.5, this is your 50% chance, or you're equally likely to happen. Okay, 50-50. If you have a number, if your probability is between 0 to 0.5, that is from 0% to 50%, this is the area where you say that it's less likely to happen, right? 25%, 30%, 40%, those probabilities are less likely to happen compared to the numbers which are between 50% and 100%. These are what we call more likely to happen. 60%, 70%, and the like 80%, those are more likely to happen. So that is the definition of probability. Okay, the denotion and such. So our probability rules or numbers are only between these. Okay, let's also talk about complementation. Take note, it's a word with the E, not with the I. Okay, complement is like you flatter someone. Complement came from the word complete, in which it will complete something. Let me discuss this in a while. So, in a given observation or experiment, an event either occur or not occur, right? Or it will either occur or not occur. Those are the only things that that is possible. So we denote the things that will not occur as a complement. We read this as a complement with this symbol here. It's to be the non-occurrence of an event A, or A does not occur there. So imagine if we're going to imagine a Venn diagram with it, we're going to imagine the square, the whole area of the square to be 1, okay, to be 100%. And then we denote an event to be a circle in this Venn diagram, and that A complement will be here. Imagine if I'm going to shade A, A alone, it will all be, this A will only be the one which will be shaded. Now, if I'm going to shade A complement alone, all of this outside of A will be shaded. Notice which part or how many percent, shall we say, which part or how many percent of the rectangle has been shaded. If we're going to shade A, both A and A complement. So clearly, needless to say, we can see that the whole rectangle is shaded when we shade both A and A complement. That is to say that probability of A plus the probability of A complement is equal to 1 or 100%. Okay, that's why it completes it, because the probability of A added with its complement will complete the whole probability value, which is going to be 100%. Okay, so probability of A plus probability of A complement is equal to 1. Hence, we can use some algebra to transpose this probability of A on the other side. We can say that the probability of A complement is equal to 1 minus its original probability. Okay, so take note of this formula. We're going to face this again in a while. There are three approaches to probability, and I will be discussing this in a while, one by one rather. Classical, we have number one, classical or a priori approach. A priori means beforehand. Relative frequency or a posteriori approach, which means afterhand. And we have subjective or personalistic approach. Okay, I think this is understood already. Let's talk about them one by one. Let's talk about classical approach. Classical approach are the is the approach and probability that arose from the games of chance. That's why probability is not that famous as a branch of mathematics, because its origins is not about solving math equations or stuff. Its origins is about solving on how to win in gambling. Okay, when Fermat and Pascal were first studying this, the main purpose was about on how to win in gambling. Okay, so that's why it's not that good. Its origins are not that good. So it depends on the assumption that all outcomes are equally likely. So the classical approach um, conditions you that every outcome, all the outcome are equal in chance. So the formula for the classical approach is here. P of E, the probability of any event E is equal to the number of outcomes in E divided by the number of the outcomes in the sample space. That is the number of total outcomes in E. Okay, so let's have some examples for the classical approach. So we will let's go back to the example when we roll a die, a six-sided die once. We have this this S, and we count what is our n of S then. So 1, 2, 3, 4, 5, 6. Obviously, that's our n of S. The number of outcomes in a sample space is 6. So we let A to be the event of getting an even number. So we have answered this in a previous video. This is our answer. And we can also say that the n of A, how many outcomes are there in A? So clearly there are 3. So the probability of A is going to be n of A, which is 3, divided by n of 6, which is 6, which is 1 over 2 or 1/2. Here we go. Okay, another example. B, the event of getting a multiple of 5. We have known this from the previous video. So how many outcomes are there in B? So we can always only see 1. So what's the probability of getting a B? So the number of sample points in B is 1. Number of outcomes in the sample space is 6. So hence it's 1 over 6. Okay. Let's call it event C, the event of getting a number greater than 6. So that's an impossible event. So the number of outcomes in C is 0. So hence, the probability of C is equal to 0 over 6, or yeah, of course 0. And for event D, in the event of getting at least a 1, so we know that it's 1, 2, 3, 4, 5, 6 from the previous video. So what's the probability of getting an event, or yeah, getting a number which is at least 1 in a single toss? So that's how many are here. So we have the n of D is equal to S, actually, which is equal to the n of S. So which is equal to 6 here, not S, 6, sorry. So we have 6 over 6, which is equal to 1. Okay, so that's how we do the examples and classical approach. So every outcome here is equal in chance. Okay, let's move on and take into consideration the relative frequency approach. We also call this a posteriori approach. The determination of probability values is based on observation and data collection, or collection of data rather. So before we can even proceed to determine the probability, we must be able to have some observations on the collection of data. We must have the data itself. Hence, it's also called empirical approach, that is practical. Okay, it already have the data itself. So there's no prior assumption that all outcomes are equally likely to happen. So the outcomes are not equally likely in chance to happen. So our probability, or our formula for the relative frequency approach, is the probability of A. Let A be any event. The probability of any event A is equal to the frequency, how many in number of outcomes are there in A, divided by the total number of outcomes, which is n. So here we go. Okay, let's see some example on this relative frequency approach. So table 2 shows that the age of the eldest child in a family are it's shown here, that the age in years is for 12 to 15, there are 8 of them. 16 to 19, there are 8 of them. 20 to 23 is there are 7 of them. 24 to 27 is 3 of them. 28 to 31 is 3 of them. 35 to, or rather 32 to 35 there's only 1 of them. So if the eldest child is selected at random from the group, what is the probability that the patient or the child is this? Let this be event A, event B, event C, event D, event E, respectively. So at least 20 years old. So in relative frequency approach, we always go back to the data that we have gathered. So at least 20 years old. 20 years old. 20 years old is here. When you say at least, we still get that. We start with the 20 years old. So we're going to highlight these numbers. And then what we're going to do is to count all the frequencies corresponding to the highlighted ones. So we have 7 plus 3 is 10, plus 3 is 13, plus 1 is 14. So this is, of course, always going to be your n, which is the total number of frequency. So what your answer is, okay, the frequency of A is equal to 14. Your n is equal to 30. Hence, the probability of A for the relative frequency approach is 14 over 30, or you can simplify this, divided by 2, 7 over 15. Voila. Okay, for letter B, between 16 to 31 years old. So we have 16 years old here, 31 years old here. So we're going to highlight these parts here. And then we're going to count our F of A, F sub A rather. So 8 plus 7, 15. 15 plus 3 is 18. 18 plus 3 is 21. Okay, then we end there. So it's 21. This is our n as always. So our probability of getting the event B is 21 over 30. We can divide this by 7, or by 3 rather, by 3. 21 divided by 3 is 7. 30 divided by 3 is 10. So hence our answer is 7 over 10. For letter C, younger than 24. Oops, sorry. Let's not talk about that. Younger than 24. 24 is here. Younger than 24 are the numbers less than 24. We have here 8 plus 8 is 16. 16 plus 7 is going to give us 23. So your F sub A is 23. This is your n here. And your probability of C then is equal to 23 on 30. There you go. Okay, let's go now to letter D. Older than 27. So here's 27 here. Older than 27 is right here. So our f sub a is only 4. This is your n. So therefore, your probability of D is going to be 4 on 30. Can we simplify this? Yes. Divide them both by 2, so we have 2 over 15. There you go. And lastly, letter E, at least 24 or younger than 24. So where's at least 24? 24 is here. So at least 24 is including that. Or younger than 24 is going to be including this. What we'll do is to include everything, to add everything, because this is an or. Okay, you can either get at least 24 or younger than 24. So imagine the word or to be adding them up. So if we're going to add them all, it's going to be equal to the total frequency. So the total frequency is 30 divided by 30 is going to give us 1, and this tells us that this probability of E is what we call a sure event. This is a sure event. Okay, so that's the relative frequency approach. Next is our subjective approach, because we call this subjective because the probability of an event is the degree of belief, gut feel, or feeling, okay, by an individual that the event will occur based on all evidence available to that individual. So this is why it's sometimes called the personalistic approach. Okay, so those are the 3 approaches to probability. Let me recall that. We have classical probability, relative frequency classical approach, relative frequency approach, and subjective approach. Our standard is the classical or a priori approach. This is our standard in probability theory. Okay. Now, before we end, we will be talking about mutually exclusive events. Now, mutually exclusive events, from the word itself, exclusive, these are 2 or more events which cannot occur together, meaning there is an impossibility that they will occur together. Observe the Venn diagram here. Say you want to go to a pet shop and you want to buy a pet. Okay, you only want to buy a single pet, and of course you both love dogs and cats. Okay, but you only buy a single pet. You cannot buy something which is both a cat and a dog in species, because they cannot be the same. Okay, in a pet shop. So since they cannot be the same, you only need to choose one. And these are what we call mutually exclusive events. Okay, there's no overlapping. There's no you cannot get both cats and dogs at the same time. I mean, a cat and a dog at the same time if you're going to get only one. So there's no common. It cannot occur together for you to get a cat with a cat and a dog at the same time, or if you're going to get a single pet only. So hence we can say that A intersection B is equal to the null set or the empty set. So this is what we call an intersection. We're going to talk about this in the next few videos. So a non-mutually exclusive events is the opposite of what we have just talked about, none. When it is possible for 2 or more events to occur together. But take note, it's not necessarily that such events will always occur. There is just a possibility that they may occur together. So for instance, we can see here, say I want to draw something from a deck of cards. Say I want to draw a single card. Event A will be drawing a heart. Event B will be drawing a king. So we can say that there is an intersection for event A and B because there is a heart, which is a king. That is the king of hearts. So it's possible for me to get both a heart and a king at the same time. That's gonna give me the king of hearts. Okay, so that is the events can occur, but it's not necessarily that will always occur. So as a bird's eye view, we can see now or differentiate mutually exclusive events and non-mutually exclusive events. Aces and kings, we cannot take at the same time an ace and a king at the same time, but hearts and kings we can. Okay, hearts and kings we can. Okay, and that's the end for our first 2 videos. This is part 1. I cut the part 1 into 2 parts. And in the next video, we're going to talk about set operations and probability. And I'm going to give one example for that. So again, please hold on and be with me in the next video. Thank you very much. Hope you would like and subscribe. Okay, see ya.